we'll continue with dimensional analysis. This is my third video on dimensional analysis. The second video I started by showing you how to derive the dimensions of some derived quantities, and then I'll continue in this third video. And I want to point out something here, that potential difference and electromotive force have the same dimension. Last video I showed you how to derive the dimension of a potential difference. So it's the same thing as electromotive force. Both of them are defined as the work done per unit charge. Okay, so they have the same dimension. Again, the dimension of potential difference is m l squared t minus 3 I raised to power minus 1, which is the same as dimension of electromotive force. Okay, let's see the dimension of other quantities, like the dimension of capacitance. How do I dimension capacitance? C, that's the symbol. Now, capacitance of a capacitor is defined as the ratio of charge between the plates of the capacitor and the potential difference. So the dimension of charge is I multiplied by T. Dimension of potential difference, we have it here already. That gives us m L squared T minus 3 I raised to power minus 1. So, but when I use the laws of indices to evaluate this, my m becomes m minus 1 when it goes up. Now this L becomes L minus 2 when it goes up. Now this is t raised to power 1 divided by t raised to power minus 3. That gives me t raised to power 4 as a dimension of and then this one gives me times I. So that gives the dimension of capacitance. This t raised to power 4 and I raised to power 1 when this one goes up. But when this one goes up, now recall that there's a current I here, multiplies this, that gives you I squared as a dimension of capacitance. Okay. Now the unit of capacitance, of course, in FI unit is a farad. So which means this is the dimension of the farad, the unit of capacitance. Okay. Okay, so let's dimension some more physical quantities. Permittivity, and that gives us from this equation, from Coulomb's law, the force that is acting on 2-point charges separated by distance r is given by Q, the product of their charges, Q1, Q2, over 4 pi epsilon multiplied by the distance. This is called the distance separating the two charges. Okay, from here we can see that 4 pi is dimensionless. So making this the subject of the equation, I have permittivity equals the product of the charges Q1, Q2 divided by F times R squared. Okay, so this gives me product of this charge is dimension I times T multiplied by I times T. Okay, that will give me I squared T squared. Okay, now F is m L T minus 2 multiplied by distance. That's the separation of the two charges. That gives me L squared. So simplifying this gives me I squared. T times T gives me T squared divided by m L T minus 2 L squared. Now, when this T minus 2, when you evaluate this using the laws of indices, you have I squared T raised to power 4, then over, we have here m. Now, this L times L gives me L raised to power 3, L times L square rather. So that gives me that. So if this goes, I have m minus 1, I have L3, I have T4, I have I raised to power 2. So that gives me the dimension of permittivity. Okay, take your time and look at it. And I want to believe I didn't make any mistake there finding the dimension of permittivity. So I want you to take your time and also look at it with me. Okay, just use this equation and confirm that I am right. Okay, that gives the dimension of permittivity. Okay, let me take some more. I'm looking at dimensions of quantities in the magnetic magnetic field. Let's look at there's what we call electric dipole moment. Electric dipole moment. Electric dipole moment. What is the dimension of this? It is given as the product of charge and the distance separating the two charges. Okay, dimension of charge is I times t, that is current times time. Dimension of distance is this. That gives me Okay, so the dimension of distance is L. So that gives me L T I. That is the dimension of electric dipole moment. Now let's look at the dimension of electric field intensity, electric field strength or field intensity, that is E. It is defined as potential difference V over D. Okay, before now we have dimension potential difference. Okay, this is my dimension for potential difference. That gives me M L squared T minus 3 I raised to power minus 1. The dimension of distance is L. So that will give me the dimension of electric field strength as M. This will cancel out this. That gives me L T minus 3 A raised to power minus 1. That's the dimension of electric field strength or intensity. Okay, so that's the dimension. For permittivity, when this L raised to power 3 goes up, it becomes A raised to power minus 3 as the dimension of permittivity. And then we have the dimension of electric dipole moment, product of charge and the distance separating the two charges. Charge has the dimension of I times T, and then D has the dimension L, that's distance. So we have this as the dimension of electric dipole moment. Electric field strength gives me this. Electric field strength is defined as the ratio of electric potential over the distance, and then that gives me this as the dimension of electric potential. Okay, so quickly, let's see the dimension of some more physical quantity. Electric flux. What's the dimension of electric flux? Now let's continue with dimension of electric flux. That is electric lines of force, also called electric flux. The number of lines of force passing through the unit area and right angles to the area. Now electric flux is given as charge over permittivity. We've already dimensioned permittivity. We have it here. The dimension of permittivity is this: m raised to power minus 1, m raised to power minus 1, a raised to power minus 3, t raised to power 4, and I squared. Okay, so that's the dimension of permittivity. Now we need to find the dimension of electric flux by dividing charge. Dimension of charge is IT divided by the dimension of permittivity m minus 1, I minus 3, T4, and I squared. So when we simplify this one cancels this. So we have this that gives us m when it goes up, then L raised to power 3, then T raised to power 1 divided by this, that gives you T raised to power minus 3, and then this gives you I raised to power minus 1 as the dimension of electric flux. Magnetic flux density. Let's see the dimension of magnetic flux density. The symbol is B. That's the B field. Some call it magnetic field strength. So it is given as this formula B. Let's use this to derive the where B is the magnetic flux density given by the force over current times length. The dimension of force is M LT minus 2 divided by the dimension of current is I, dimension of length is L. So this cancels this. That gives the dimension of magnetic flux density as M T minus 2 and I raised to power minus 1. Dimension of magnetic flux density. You can do that for the dimension of magnetic flux. Magnetic flux is also a measurable quantity in physics. Magnetic flux is the product of magnetic flux density and area. You also multiply this by area. That gives you the dimension of magnetic flux, which is m t minus 2 L squared I minus 1. Or you can bring this before this. That gives the dimension of a magnetic flux.